All right. Maybe I'll get this adjusted. Okay, at the end of the last lecture, we came up with a formula for the multiplicity of an ideal gas of N particles. And remember first how this worked out for a single particle. If we have just one particle, the multiplicity formula is pretty simple. Let's see here. Where this is the volume, that's the volume of the momentum space, and then h cubed is Planck's constant cubed. And of course, the volume of momentum space gets into, there are some numbers running around in there, and we've got a dependence on the square root of the energy. But it's going to write it down for N particles, where we've worked out what all that is. So we have taking some approximations, because N will generally be a large number. So it would be written as an exponential, maybe a mole of something, 10 to the 23rd power. And we can ignore subtracting off 1 from that, which comes up in the formula. So 1 over n factorial, this factor of 1 over n factorial is to account for the fact that if we take any two particles in the gas, which are identical, and we give them the same momentum direction and magnitude, the same momentum vectors, but switch their positions, then you've got the same thing. Or if we exchange this particle with that particle, with everything else being the same with that there, that does not change what the state of the gas is. So we divide by that there, which is the ways of exchanging them. And let's see, our formula then is volume to the nth power over h to the 3nth power pi to the 3n over 2 over 3n over 2 factorial and then 2mu to the 3n over 2 power. It's ugly, but the dependence of the multiplicity on the volume and the energy is actually fairly simple. And we can sweep all the other ugly stuff that depends on n, like a factorial, which we don't like, and n popping up in these exponents. We can sweep all of that into just some generic function we'll call f. So it's some function of n times v to the nth power times u to the 3n over 2 power. Okay, and that's good enough to describe the functional dependence on what we're interested in. All of the other constants, like 2m here and h bar, h to the 3n and pi, fall into that function there. Okay, I like how the book puts it, where f is a complicated function of n. Okay, let's see here. He makes a note that the exponent of the energy is 1/2 times the total number of degrees of freedom for a monatomic ideal gas. So a monatomic ideal gas has 3 degrees of freedom for every molecule, every particle in it. And so for n particles in the gas, you have 3n degrees of freedom. So it's 1/2 times the number of degrees of freedom for the monatomic gas. He says, note that the same is true of the multiplicity of an Einstein solid in the high temperature limit. And these are both special cases of a general theorem that for any system with only quadratic degrees of freedom, having so many units of energy that you don't need to worry about quantization. That's why we took the high temperature limit for the Einstein solid. So if we don't have to worry about the quantum mechanical nature of it, because we've got a whole lot of particles, or a whole lot of energy, then the multiplicity will be proportional to u to the nf over 2 power, where nf is the number of degrees of freedom, lowercase f there, degrees of freedom. So that's actually a nice little theorem right there. Okay, but what we're going to do today is allow the ideal gases to interact with each other, just like we did earlier on in the chapter with 2 Einstein solids that were interacting, exchanging energy. In the case of ideal gases, we could exchange energy, we could allow them to exchange volume, and we can allow them to exchange particles, which is something we couldn't really do practically with the Einstein solids. Or it's easier to with the gases. So, let's say that we set up I've already written that there. Let's say we set up a container and we've got, it's insulated, so there's no interaction with the outside world here. And on one side of the container, we have gas A, and on the other side we have gas B. Now, A and B are divided by a little screen there, a thin wall, which keeps the gas molecules of A in their place and the gas molecules of B in their place. And this wall does not move, so the volume of A is fixed and the volume of B is fixed. But what they can do is, let's say it's a thin aluminum foil barrier. So it's thin enough that it allows them to radiate energy across it in the form of heat. So a little wavy line is energy, and it can go from one side to the other freely. Okay, so we have some amount of energy for A, and some volume for A, and some number of particles in. Let's say that we've got the same number of particles for A and for B, just to make the notation a little simpler. So B has some amount of energy, it has some volume, and it has a number of particles in as well. Okay. Now, the multiplicity of the total combined system is the product of the multiplicity of A and the multiplicity of B. So we'll say omega sub total is just omega A times omega B. Well, all I've got to do then is to multiply this formula with a subscript of A for V and for U, times the same formula with a subscript for B for V and for U. N is the same for both of them. All right, so if I do that, then, let's see, I'll have a function of N squared, because I've got it for both of them. It's not an N squared, it's the function squared of N. There we go. Then I'll have V sub A to the nth power times V sub B to the nth power. So that's just VA, VB, all to the nth power. And then I'll have UA to the 3n over 2 power times UB to the 3n over 2 power. So I can combine those. UA times UV to the 3n over 2. Turn the camera a little. Okay. Now, if you take a look at the interacting Einstein solids back earlier in the chapter, it's the equation 222. On page 64, we get a similar result where we have, let's see, similar form, you should say. You've got the energies raised to a large exponent. So, when we talked about the Einstein solids interacting, we looked at what was the probable state of the combined system to be in. So we looked at, as a function of the energy of Einstein solid A, how many units of energy did it have? Then we looked at the multiplicity function of the combined system as the multiplicity of the combined system as a function of the energy held by part A. And we found the most probable state for that to be in, and that there was a very narrow range when you had a large system that was really probable for it to be in. We'll do the same thing here. So we'll take a look at what's the multiplicity, meaning the possible states, microstates, for the combined system to be in as a function of the energy in system A. Because they can exchange energy, then A can have a little more and B can have a little less, or B can have a bit more and A can have a little less. But the total must stay the same. Okay. And if you go through that, which we're not going to do, we're not going to derive it out because it's really following the same thing. Then what we find is there's the multiplicity of the whole system is essentially 0 for just about all possible states except for a very narrow peak and the width of the peak is the total energy divided by the square root of 3n over 2. Now keep in mind, if these two can exchange energy but they can't give it up to the outside world, then the total energy is fixed. So this total energy is just UA plus UV. So the width, which gives you a feel of what range of outcomes are really probable, the width is pretty narrow because we're dividing some fixed amount of energy by a large number. So we get the width is a very small number. Okay. Now we could set it up to where instead of exchanging energy, we're exchanging energy and we're exchanging volume. Let me draw what that situation would be like. So this one was exchanging energy only. Now we exchange energy and volume. In this case, we're still insulated compared to the outside world, and we've got a container of a fixed total size. It's a thin membrane that allows the energy to transport across it, so you can have heat flow one way or the other. But you can also have that barrier slide back and forth. Let's say it's a piston inside a cylinder. It can freely slide. So the whole thing can shift left or right. Now the funny thing is, when we say exchange volume, we're not used to thinking of volume as a thing that can be given up. But imagine it this way. The total volume inside here is fixed. But if this barrier slides to the left, A has less volume and B has more, but the total has stayed the same, which is the normal way we would think of it. But you can look at it as A has given up some volume to B. Or if the barrier slides this way, B has given up some of its volume to A. A's particles still stay on the left-hand side of the barrier, and B's always stay on the right, but the volume has been exchanged between them. So we can exchange energy and volume, but the total energy is the sum of the two. And the total volume is the sum of the two. In this case, we would still get, if we look at it as the multiplicity as a function of the total energy, of the energy of, say, part A, we would get exactly the same result we had before. That the multiplicity function peaks with respect to the energy of A with a width given by that. We've already done that. That doesn't change. But if we also allow an exchange of volume, then we can plot the total multiplicity as a function of the volume of A. And just as before, it has a peak with a very narrow width. And it comes out to be V total over the square root of N. Think about this, by the way. The functional dependence of the multiplicity on V, it's V to the nth power. And the width here, when we look at the multiplicity as a function of VA, the width is V total over the square root of N. The multiplicity function has V to the nth power, so we're taking V divided by the square root of its exponent. Over here, when we were exchanging only energy, we have U over the square root of 3n over 2. Well, the functional dependence of multiplicity on U is U to the 3n over 2 power. So in both of these cases, we're dealing with Gaussian functions where the width is given by whatever variable we're talking about, divided by the square root of its exponent. On the other hand, the dependence on number is a complete and utter mess. So, if we want to exchange particles, well, we would have a, I'm going to draw it anyway. Okay. Exchanging particles means exchanging number. So now we've got U, V, and N. We're still including U and V as things that we can exchange here. So the total number is still conserved. It can't be exchanged with the outside world, but it can be exchanged between A and B. Now let's make it a permeable membrane, where particles can, maybe with a little bit of time, or maybe very quickly, they can individually move over here. And we can still exchange energy, and we can exchange volume. I won't draw the other arrows on there, I'll just tell you. Okay, in that case, we would apply the same kinds of reasoning, and we would find it was a real mess because of the complicated functional dependence. But, yeah, you would have a narrow peak as well. Let me see here for any extra comment I should make. Just, it's complicated. So, but you would still have a narrow peak. As a function of the number held on side A, like that, and you'd have a narrow peak. Now, that still tells you that there is a single state, which is very likely for the system to be in terms of a number, and the single state in terms of volume, and the single state in terms of energy for, say, one side or the other. And all the other states are very, very unlikely, except for extremely small changes around this. Oh, by the way, when you're exchanging particles, you might wonder, why do I still have the barrier at all if the particles can move freely through it? What's the point of even having it? Why don't we just get rid of it? Well, if we got rid of the barrier, we wouldn't be able to say where is side A and where is side B. A can give up particles to B, now they are on side B, and that way you can keep track of one region versus another. It's not A's molecules anymore, it's just the things on side A. Okay, when do things come to equilibrium? Well, when you have energy exchanged, equilibrium, when things become stable and they stop making overall large-scale changes. When the system comes to rest, to equilibrium, at the most likely state in terms of energy, is when the temperature is the same on both sides. So exchange of energy, temperature is what drives it to equilibrium. Same temperature on both. If you're exchanging volume, when they come to equilibrium in the most likely macro state, where that peak was, is when the pressure is the same on both sides. Which makes some sense. If you've got a piston that can slide back and forth, and you've got a high pressure on one side and small pressure on the other, it'll slide around until the pressure is equalized on both sides. And we've got an instinctive feel for that. Probably better than either of the others. And if you can exchange particles, it comes to an equilibrium here when the density is the same on both sides. Okay, so there's a nice symmetry among how these three ways of exchanging things go. All right, now let's do something useful with this. Let's take one of these boxes, containers, and we've got sides A and B. We've got the permeable barrier, so particles can flow through it. We could even just have an invisible line down the middle, so that we're keeping track of what's side A and what is side B. So here's the question. What is the chance that all of the particles will wind up on side A with none on side B? Just as they're bouncing around, what are the odds we'll ever find it this way? Very small. But now if we've got one particle, half the time it's going to be on that side. If we've got two particles, probability starts going down. Three particles, it's way down. And when we get to 10 to the 23rd power, we've got a mole of something. It's really rarely likely to happen. Well, how rarely? Okay. What we can do is, if we start off with A having N molecules and B having N molecules, then what we're asking is the chance that we have 2N on side A. Trying to think if I'm setting this up correctly. Okay, yes. A way of calculating this then, it's the same as if our original gas with 2N particles occupied by random chance half the original volume. So let's say that these are, these have equal sides, equal volumes on each side here. So let's say the multiplicity as a function of energy, volume, and number. I think this is makes it, the book is not unclear, but I think this will make it even clearer to find what the probability is. Write out the multiplicity as a function of u, v, and n. Okay, so that is a complicated function of n, v to the nth power, and u to the 3n over 2 power. So what's the multiplicity then of the system having the conditions total energy U, volume V over 2, and number N? See, in general, we just label the energy by U, and we label the volume by V, and we label the number by N. But what if the volume is some amount V over 2? Okay? So that's f of n. V over 2 to the nth power, u to the 3n over 2 power. What I want to do is to recreate this up here. I know what this is. This is the multiplicity of the system occupying u, v, and n. So what can I do to make this back into this form times something, is what I'm hoping for. Well, I can factor this out here. I can take, factoring it out, I guess, 2 to the minus nth power. It's 1 over 2 to the nth power times v to the n. So it's 2 to the minus n. There. I think I did that right. So that's 2 to the minus nth power times, well, f of n, v to the nth, u to the 3n over 2 is the multiplicity of a system with energy u, volume v, and number n. So, there, what I can do is take the ratio of those two multiplicities. I can say that, well, there are two ways to say it. The multiplicity of this system occupying volume v over 2 is 2 to the minus nth power times the multiplicity of the system occupying volume V, the full original volume. Or for that matter, I can take the ratio of those multiplicities is 2 to the minus nth power. The ratio of multiplicities is the ratio of probabilities. Multiplicity is not probability. You've got to divide by the total. But a ratio of multiplicities is the ratio of probabilities of finding it that way. So what are the odds this would happen if we had one molecule? One molecule. Say that? Well, I mean, what are the chances? What's the probability? The ratio of multiplicities is the probability of finding it that way, in this way versus that. So it'd be 2 to the minus 1 power, 1/2. Half the time it'll be on half the side. What if we have 10 molecules? 2 to the minus 10th power. If we have a mole of them, 2 times 2 to the negative 10 to the minus 2 to the minus 10 to the 23rd power. I mean, this is one of those things. The book actually does a roundabout calculation and says if you have 100 molecules, which is we could draw that up there. I got partway there drawing it there. For n equals 100, the probability of finding them all on 1/2 of the side, one side becomes less than 10 to the minus 30th power. And so, since the universe is about almost 14 billion years old, if you count the number of seconds in the universe, you would have to check the system 1 trillion times every second for the entire age of the universe before you have a chance of finding it this way one time. So when you've got a mole of gas molecules bouncing around in there, the chances that you will ever find the system in this state is vanishingly small. It's already vanishingly small for a relatively small number of particles. Okay, so this is how we see that when the system comes to equilibrium, it's in a really very likely state, and we are really unlikely to find it in any other state when it is in equilibrium. Okay. What we want to do with this, we don't like dealing with these factorials, and this complicated function of n here is a mess. Luckily, in practice, we are not usually dealing in regular everyday life with the multiplicity of systems, but rather with the entropy. And the entropy, see here, I'm slightly cut off. Okay. Just for a quick view of the equations I've written up there. All right. The entropy is, let me see here. I'll read this out. For any large system in equilibrium, will be found in the macro state, that's given a certain energy, volume, number, temperature, say, things like this. The macro state that has the greatest multiplicity, aside from fluctuations around that peak that are just too small to measure in practice. This is a general statement of the second law of thermodynamics. Simple form of that is multiplicity tends to increase. If you start off the system in some unlikely macro state, something that has a small multiplicity, fairly soon you're going to find it in the macro state with the greatest multiplicity. So it will tend to increase. But if you start off in that very likely macro state that has a peak of multiplicity, you're unlikely to find it ever going to a lower multiplicity macro state. So the multiplicity tends to increase. This is simply a statement of probabilities. It's more likely to be found in states than it's more likely to be found in, which is almost a tautology. Okay, so in working with it in thermodynamics terms, easier than working with multiplicity is working with the entropy. K log omega, where K is Boltzmann's constant, which is, according to the front inside cover of your book on the top, 1.381 times 10 to the minus 23rd power joules per Kelvin. A very small number. But remember, when in the, like in the ideal gas law, when we're dealing with particle systems that have maybe a mole of particles to them, where you've got a 10 to the 23rd power, that will cancel out with the 10 to the minus 23rd here, and you get numbers that are close to order unity. Okay, Boltzmann's constant, and of course, omega is the multiplicity. So by taking the natural log of the multiplicity, we can use Stirling's approximation to get rid of those factorials, and we can also make it into a much more manageable formula in other ways. I believe, by the way, that this formula was put on Boltzmann's tombstone. If you ever want to have anything on your tombstone to be famous by, this was his. It's a nice simple statement there. I mean, entropy was understood as something that drove a system to equilibrium before they understood what it really was. And I believe it was Boltzmann's insight that it had to do with the multiplicities, the number of ways the system could arrange itself in. There were other, I believe, other attempts at defining entropy before that. This really got down to what was going on at the microscopic level. Okay. Now, let's see. Omega, multiplicity, is unitless. So you take the natural log of it, you've still got a unitless number, dimensionless. And so since Boltzmann's constant has units of joules per Kelvin, entropy will have units of energy over temperature, whatever system you're dealing with. Okay. So if you've got, for example, the Einstein solid in the high temperature limit, let's see what the entropy would be. Okay, Einstein solid with the number of quanta of energy much larger than the number of oscillators, so the high temperature limit. And in that case, recall that the multiplicity was on the order of, and this, whenever I use a single squiggly line, it's used in a few different ways. Sometimes it means a very rough estimate, where we're even ignoring factors of 5 or 10 or whatever like that. Other times, people sometimes use it even to mean proportional to, which is really should be written more like that. But order of magnitude or worse there. So we've got something on the order of EQ over N to the nth power. All right, let's find out what the entropy is. Let me erase Boltzmann's constant here to give myself room. Let's see. I've already got S equals K log N. So, S equals K times the natural log of EQ over N to the nth power. What's the first thing I should do with this? Even before that, right. Take that exponent, multiply it out front of the natural log. Nk, and you're going to be seeing a lot of Nk multiplied together, times the natural log of EQ over N. Now what do you do? Right? So if I've got a product inside the logarithm, then I'll have the sum of two logarithms, and a ratio then will give me the difference in the logarithms. Okay, log of E plus log of Q minus log of N. What's log of E? Natural log of E. Nope, it is something. It is 1, that's right. Okay, 1 plus, tell you the truth, log of Q minus log of N doesn't really get me anything extra. I'll just leave these two in a ratio. Really what this was useful for was getting rid of that log of E. Let's see, that's the state I want to get it into. Yep. So the entropy of a hot Einstein solid becomes a nice simple formula. Nk, remember where Nk in laboratory scale situations is going to be close to order unity. You might have 10 to the 23rd particles, and you've got 10 to the minus 23rd here. Times 1 plus log of Q over N. Both of those are large numbers. All the Q is much larger than N. So this natural log here is going to be a positive number. Okay. What about then? Let's see. Yeah. If we have, plug in actual numbers here. I think I can fit this on. If we have something less than a mole, let's say 10 to the 22 oscillators in our Einstein solid, which would be a small but visible system. If we looked at it, we could see that. And we have 10 to the 24th energy units. Okay. Then, let's see, Nk, so that's, let's see, Nk, that's all showing up. 10 to the 22 times, what was K? I've erased it now. What is it?
1.381 times 10 to the negative 27.
Okay, and the units? Joules per Kelvin. All right. Times, I'm not sure if this can turn any more. Let me see if I can get it on. That's all I can read. 1 plus natural log of Q over N, so that's 10 to the 24 minus 22. All right. That's 10 squared, so that's natural log of 100. What's the natural log of 100? 4.61 plus 1 gives us 5.61. And here we've got 1.381 times 10 to the 22 minus 23, so that's 10 to the minus 1 there. And, joules per kilogram. So that's actually a pretty easy number to do. We're going to get something slightly less than 1. And what do we wind up with? Okay, 0.775 joules per Kelvin. That's the entropy of an Einstein solid, which is, just a model of solid matter, maybe about yay big. That's warm to hot. A little less than 1 joule per every degree Kelvin. That's how much energy per temperature. All right, this is a nice human scale type number. Whereas we were dealing with the individual numbers that go into it are just astronomically large or astronomically small, if that makes any sense. Okay. Okay, 1045. I get mixed up with Mondays and Thursdays now. Another property of entropy. Swing back around here. Well, multiplicities, if you have a system made out of 2 parts that are in contact with each other, well, even if they're not in contact with each other, if you have the system made out of 2 parts, the total multiplicity is the product of the multiplicity of A and the multiplicity of B. So, if I have it here, so the entropy of the total system is that. But if I put in that this is the product of the individual multiplicities, take the natural log, you wind up adding those. Well, this is simply the entropy of part A, and that is the entropy of part B. So we wind up with a very neat result. that entropies add. If you have two parts to a system, you can simply add their entropies and you get the total entropy. Okay. A few statements, which it's not worth writing up there, but I'll speak. Multiplicity gives you the number of ways the system can be arranged at the micro scale for any given macro scale description of it. So it gives you the likely state for the system to be in. Entropy is, of course, just the k times the log of the multiplicity. So we tend to think of entropy being the disorderliness of the system. There are more ways for a system to be disorderly than there are for it to be very neatly ordered. But we've got to be careful there because it depends on what you mean by ordered or disordered. He gives an example. Let's see here. The more particles there are in a system and the more energy the system contains, the greater its multiplicity and the greater, therefore, its entropy. Besides adding particles and energy, you can also increase the entropy of a system by letting it expand into a larger space, because now it's got more room to arrange itself in more ways, or by breaking large molecules apart into small ones. So you break pieces of the system apart. Now they're not constrained to be attached to each other. They can be arranged in a lot of different ways. Or by letting to mix together things that had been separate. As an example, taking a bucket of water and a bucket of ink. Separately, they are unmixed. They've got a certain entropy. But you dump the ink into the water. Now there are a lot more ways that the molecules of ink, can be arranged in between the molecules of water. Being completely separated is obviously they're unlikely to unmix themselves, for example, except by maybe the action of gravity or something like that. But if we're not paying attention to that, but so they're unlikely to be back into the separated position. That's a very unlikely state to be in. So you wind up increasing the entropy, putting them into a more equilibrium state by mixing them. Let's see. So because we think of entropy as being disorder, he says, be careful about what you mean by disorderly. Most people would agree that a shuffled deck of cards is more disorderly than a sorted deck of cards. There's only one way that they can be sorted in order. Well, maybe there are a small number of ways, depending on which way do you want them sorted. In order of increasing numerically, or you can have decreasing, so there are maybe two ways there. You can have a bunch of test papers, put them in alphabetical order. So there's one way, and that's orderly. If you've got them all shuffled up randomly, that is disorderly because there are a lot of different ways they can be out of order, but only one way they can be in order. See what that means then? So the entropy is larger for this disordered random looking state. So shuffling cards increases their entropy. But if we just think of it as disorderly, then compare a glass of crushed ice, frozen crushed ice, with a glass of water. So instinctively, we might think of the crushed ice as looking more disordered. It's all in a jumble, where the water looks nice and even and very ordered. But the entropy is certainly higher in the glass of water, because the individual molecules of water have a lot more ways they can arrange themselves than they did when they were in a glass of crushed ice. Crushed ice, the fact that they're frozen in position means they are stuck there. And you can only rearrange those chunks of ice in large parts. All these molecules frozen together in one chunk of ice have to be together. So they don't have the freedom to go and mix around with the others. So you've actually got quite a bit of lower entropy in the crushed ice than you do with the water. Okay. Let's see here. So we can restate the second law of thermodynamics on page 76 as being that any large system in equilibrium, and that equilibrium is key, will be found in the macrostate with the greatest entropy, aside from small fluctuations around the peak, which will be very hard to measure for a large system. And he says, or more briefly, entropy tends to increase. And you should put a star by that statement, entropy tends to increase, because entropy will be the driver of the system to equilibrium.